In today's lesson, we're going to combine what we did last lesson on the work on radians and what you did last year or at GCSE about arcs and sectors. So let's recall what we know from GCSE about arcs and sectors. We know if we've got a full circle, then the length of the arc is the circumference, so that's pi times the diameter, or 2 pi times the radius. And if we want the area of the full circle, we can use pi times the radius squared. If we're just working with this sector, if the angle at the centre is theta, then we've got theta out of 360 degrees. So the fraction of the circle contained within our sector is theta 360ths. So our arc length is theta 360ths of the circumference, and the area of our sector is theta 360ths of the area of the whole circle, pi r squared. Now we want to be working in radians, so instead of using 360 degrees as the angle at the centre of the full circle, we need to consider that in radians. From last lesson, we know that 180 degrees is pi radians, so 360 degrees is 2 pi radians. So to write these formulae in terms of radians, we just replace the 360 degrees with 2 pi. Now if we look at the arc length, we can simplify this expression because we've got a divide by 2 pi and a multiply by 2 pi. So it will simplify simply to theta times r, which we normally write as r theta. The area expression doesn't simplify quite as far. We've got a divide by pi and a times by pi, so those will cancel. And then we've got theta over 2 times r squared, which we normally write as a half r squared theta. These are the expressions that we use for the length of the arc and the area of a sector when we're working in radians. So if we look at the notes for today's lesson, the top box just contains the information that we've just discussed. So when you've got this sector, radius r and angle theta, the arc length is r theta, the area of the sector is a half r squared theta. And working with this, we'll get to a point where we just remember that. But if we can't, then we can always derive it like we've just done. Let's look at some examples. So example 1 is very straightforward. It's just substituting into those formulae. So question 1a, find the length of the minor arc. The minor arc means the shorter arc. So we're looking at this bit here, as opposed to the major arc, which would be this long arc here. So if we want the length of the arc, we just use r theta. So our radius is 15. Our theta is 1.6 radians. So we just need to do 15 times 1.6, which is 24, and we're working in centimetres. For part B, we want the perimeter. So we've worked out the length of the arc. For the perimeter, we need to add on the other edges of the sector as well. So that's just the 15 and the 15. So that will give us 54 centimetres. And then for the area, we need to use a half r squared theta. So that's a half of 15 squared times 1.6. I think it's time to bring a calculator out. So half times 15 squared times 1.6 gives us 180 centimetres squared for our area. The next question takes it a little bit further because this time we want the area of this shaded segment here. So remember, a sector is like a slice of pizza. A segment is the region between a chord and the circumference. So we're wanting the area of this segment. To do that, we can work out the area of the sector and subtract the area of this triangle here. The area of the sector is a half r squared theta, so a half times 6 squared times pi over 5, and that gives us 18 pi over 5. I'll leave it like that for now so that I don't have to do any rounding and lose any accuracy. For the area of my triangle, we can just use a half AB sine C. Remember, for a half AB sine C, you need two adjacent sides and the angle contained within those sides. So we've got two adjacent sides and we've got the angle between those sides. So it's just a half times 6 times 6 times sine pi over 5. Now remember, you must have your calculator in radians because you're about to ask your calculator to work out sine pi over 5. So your calculator needs to know that pi over 5 is measured in radians and it's not measured in degrees. So make sure you've got the R at the top of your calculator screen. Remember, you can change that by pressing Shift Setup and then option 2 for angle units. So we need to make sure we're in radians. So I'm going to have half times 6 times 6 times sine of pi over 5, and that gives us 10.58. So the area of the segment is the difference between those two. So I'm going to use the 10.58 as accurately as it is on my calculator. So I'm doing 18 over 5 pi, take away my previous answer, and I get 0.73. And we were working with centimetres, so the area will be in centimetres squared. So that is just a tiny slither there, it's got a very small area. For question 3, we're working in reverse. So we've been told the arc length of this sector is 24 pi. Remember, arc length is r theta. And we're told that the area is 216 pi. So a half r squared theta is 216 pi. And we have two unknowns in two equations. So this is simultaneous equations, but not like any simultaneous equations we're used to seeing. Now if I label this equation 1 and this equation 2, this equation is a multiple of r theta. So I could divide a half r squared theta by r theta and divide 216 pi by 24 pi. So I'm doing equation 2 divided by equation 1. We're not used to doing that, are we? We're used to adding and subtracting them in order to eliminate a variable. But in this case, division eliminates a variable. So if we have half r squared theta divided by r theta and 216 pi divided by 24, then on this side, the thetas cancel and one of the r's on the top cancels with the r on the bottom. So we have a half r. Missed my pi off. Our pi's will cancel on the right hand side, so we've got 216 divided by 24, which is 9. So half r is 9, so r must be 18. And we had our area and our arc length in centimetres squared and centimetres, so our radius must be in centimetres.